Okay, well, finally, after we sorted out the hydrodynamics, we can go to the sediment concentration. And here is the sediment concentration, the advection diffusion equation in 3D. So in the case where we resolve the whole 3D dimensional flow, then we have the usual rate of change of the concentration C, the advection of the concentration in x and y direction. The vertical advection, in the 3D case, we also have, even though they're small, vertical velocities, but we also have the fall velocity of the sediment. And that matches the vertical diffusive flux plus the horizontal diffusion. This has a boundary condition of the sediment concentration at the bed level as a function of the shear stress, and the shear stress is a function of the velocity and maybe the orbital velocity. With this kind of equation, we can resolve very subtle changes in the velocity and concentration pattern. For instance, here we have a logarithmic velocity profile that is the flow is coming in through a flume, and the flow doesn't suspect anything, but then suddenly there's this trench, and you see the flow here takes a while to advect from here to the bottom. And once it gets out of the trench, the flow profile is relatively contracted. So here the flow near the bottom is relatively strong. And if we go a little bit further again, then finally we have a situation where we go back to the logarithmic velocity profile. Similarly, the concentration profile here, it is not as steep as here, because the stirring up here is much less. So there's basically sediment settling out here. You see this again, the model captures this fact very nicely. And here again, there's an accelerated picking up of new sediments as this flow is so concentrated near the bed, until finally the concentration goes back to the usual Rausch profile in a logarithmic velocity profile. For many cases, we don't need to solve everything in 3 dimensions, and we're mostly interested in the horizontal patterns of the flow and the wave-driven currents. In that case, we can simplify the advection diffusion equation to a 2-dimensional advection diffusion equation for the depth averaged concentration. And what you see here is that the source term now, this is an approximation that instead of resolving exactly what happens near the bottom, we assume that the concentration wants to go to the equilibrium concentration with a certain time scale. And this time scale is related to the water depth divided by the fall velocity. Again, this equilibrium concentration is a function of the bed shear stress, and the bed shear stress is somewhat related to the near bed velocity. And this equilibrium concentration can be computed using various approximations according to several sediment transport formulas. And so if you divide the sediment transport by the water depth and by the mean velocity, you get this average equilibrium concentration, which goes into this equation. So how does it work? For instance, if you start from rest and you suddenly you have a flow, then there is the actual concentration is 0, but your equilibrium concentration would be a direct function of the velocity. And so this will mean that sediment will be picked up from the bed. This will be a positive term, and then that will be advected and will lead to an increase in the actual concentration until the whole situation becomes equal to the equilibrium concentration. Okay, we've figured out how to do the hydrodynamics and the sediment transport in a two-dimensional model now. But now let's see how we can turn this kind of simulations into a long-term or medium or long-term morphological model. We're going to be talking about different approaches, including morphac and more merge and all that. So basically 3 kinds of approaches. The classical, we call it tide averaging approach. Then we switch to a more modern elongated tide or morphac approach. And the most modern method we have is the parallel online method, also called more merge. So let's start with the standard setup as it was developed since let's say the 1980s and early 90s, valid both in depth averaged and 3D mode, quasi 3D mode. So as we started with this lecture on morphological area model, process-based models, and we start with the bathymetry, we go, of course, the boundary conditions change the whole time. We do flow and wave and flow simulations that are coupled together. They lead to transport, and that then leads to so-called initial sedimentation and erosion patterns. And we don't just stop there, but we say this is bottom change, which we feed back into the bathymetry. And there is a quick loop that just does a simple adaptation of the sediment transport directly based on the bottom changes, but a slower loop that is, well, after a couple of these intermediate transport steps, we have to update the whole bathymetry, the whole wave and flow simulations again. This very often was done in a way that we ran, given a bathymetry, we ran flow and waves over a whole tidal cycle, then computed the transports over the whole tidal cycle, did an averaging over the tidal cycle, and computed the bottom change averaged over the tide. And often we would multiply this bottom change by a number of tides to speed up the time. And so we would not do one-in-one this loop, but first stop after a tidal cycle, collect the transports, do tidal averaging, and then compute the bottom change based on that. That's why it's also called the tide averaging method. So the tide averaging approach. Let's try to understand what we're doing with that by following these formulas. What we want to compute is the overall change in the bathymetry after a number of tidal cycles. The tidal cycle has a period of t, and n is the number of tidal cycles. So basically we have to integrate dz b dt, the rate of change of the bathymetry, over time. And we can write dz bdt as minus the gradient of the sediment transport. This nabla vector indicates the sx dx plus the sy dy. So far, no real approximations are made, but what we need to consider is that the sediment transport varies as a function of the tidal forcing and whatever, wave forcing, but also because in the meantime the bottom changes. So between 0 and n tidal cycles, the bottom is going to change. Now, the major approximation that we make in this tide averaging approach is that we ignore the change of the sediment transport because of the bottom changes within that tidal cycle. We do take into account the variation of the transport with the tide, but we average over that. So what we get then is n times the tidal period times the gradient of the average transport. Now that is, and then the hope, of course, is that these changes are relatively modest and that we can use a big N, so we only have to recompute the sediment transport. Well, not every tidal cycle, but maybe every 10 tidal cycles. But then we do make one big bottom update after those 10 tidal cycles. Here's an example of an application of this method in one of our early attempts. And what we are supposed to see here is, oh yeah, what we're seeing here on the left is the measured changes. I hope you can see it. You see this shoal moving eastward and this channel moving a bit westward, expanding westward. And if you're very kind, then you can see similar things happening here. You see this shoal moving eastward and you see this channel extending a bit. You see also these changes in the channel patterns here. Now, I have to say that we painted this in very gentle colors so that you don't really see that this yellow means that this bar actually becomes dry. So the evolution here is much more extreme than it was in the measurements. The channel gets way too deep also. But still, a number of promising features were captured in this method. However, it has some pros and cons. Conceptually, it's easy. You just do the averaging over a tidal cycle and then you do a big morphological step. You can do an update of the transport. I haven't gone into details of that, but with a relatively cheap continuity equation. And you don't need a tight coupling. Oh, that's not very important. The disadvantage is that the morphological time step is governed by the bed celerity. That is, the B is the power in the transport formula. S is the absolute transport rate, and H is the water depth. Now, if you have a high transport or a small h, the time step can become very small and actually less than the tidal period. And of course, that is not very efficient in tidal inlets. And this very shallow water happens in a lot of places, and often you do also have high transports there. So where this method is very efficient in relatively deep water, for instance, if you look at the effect of a breakwater extension or so on the scour hole, in a tidal inlet with very shallow areas, this is not a very nice method. So at some point we came to the so-called online approach, where we have a much more tight coupling between flow, transport, and bottom change. These used to be in different modules, but nowadays in Delft3D, for instance, they're all, also in XBeats, they're all in the same program actually. So every time step you go through flow, transport, and bottom change. And now and then we couple with the waves and feed information to the wave model, and the wave model feeds information back to the flow model. And this loop goes on and on. Wave boundary conditions vary in time, flow boundary conditions vary in time. Now, if you would do this thing exactly as I'm saying now, then you would have to solve, let's say, 700 tidal cycles per year. And that because there are about 700 tidal cycles in a year. And that would take a great amount of time, especially if you realize that usually the amount of bottom change in one tidal cycle is millimeters to maybe centimeters. So you do this whole thing of updating the flow and wave patterns based on the changed bathymetry, only because it has changed by a centimeter in water depth of maybe 10 meters. That doesn't make sense. So what we do is we speed up the morphological changes by a so-called morphological factor, or MORPHAC. We can easily do that by a factor of 10 to 100 or sometimes thousands, depending on how much or how little happens in one tidal cycle. The idea is that if very little happens in one tidal cycle and you multiply it by 100 and still relatively little happens, then you're okay to do that. In fact, what we're also doing is we're elongating the time. The tidal cycle, so instead of simulating 700 tidal cycles in a year, we may be doing only 7 cycles in a year. And continuously we do the updating multiplied by a factor of 100. That, you might think, is quite a bold step. Now let's do a test case here. Here's a real life case where we wanted to study the scour in front of the IJmuiden harbor. This blue thing is a scour hole as it was measured after 8 years. And we have simulations here with a 2-dimensional model and a 3-dimensional model. We have a morphological factor of 20 or 100. And here we go from 2D to 3D. You see, between measured and 3D, that's not, well, it's not the same, but there is quite some agreement here. Also between 3D and 2DH, there is some agreement, but you see, for instance, these patterns are much sharper, and the 3D model tends to smooth out some of these evolutions. But what you also see is whether we use a morphological factor of 100 or 20 basically makes no difference at all. If we follow, well, this A should be here and B should be there. So A is in the scour hole and B is in the deposition area. If we follow those in time, then the scour hole, here we have 2D between morphac of 20 and 100, basically the same. The only thing is that with a morphac of 20, it's almost continuous, and morphac of 100, you see a little bit of this accelerated tide. And we cover 8 years here, 8 times 7 per year. So we have about 56 little thingies here. Yeah? You hardly see it. So basically what this tells you, there's quite a difference between 3D and 2D simulations, just from the physical point of view, but whether we approximate it with an elongated tide with a factor of 20 or 100 doesn't make any difference. And this is what we see time and again. Unless it's extremely dynamic, we usually get away with morphological factors in the order of 50 or 100. Now, one of the problems that you still have if